Okay, so let's get started. So we missed the previous class, and then as I promised, as I mentioned, so I plan to post the recorded video during this weekend. Okay. Okay. So the the weather is back to winter. So, okay. Okay. So let's get started. So what did we learn in the previous class? So we learned about the performance of a computer system. So actually, so we learned about the CPU time, okay, the CPU execution time. So what is CPU time? So this is the execution time without any overhead, any performance overhead from the I/O devices, operating systems, and then any other applications. So this is the pure. So only one application is executed by CPU without any interventions, and then we can measure the execution time. So it's a time gap, so time difference between the start time and end time. Okay. So and then okay. So so we learned that we can just measure. So we can just measure the CPU time by counting CPU cycles, right? So it is because the CPU is a digital system, and then all the all digital systems work with a clock signal, right? So clock signal is the periodic signal. So by counting this number of clock cycles, then we can measure the CPU time. So and then so also you need to remember that the performance is inverse of the CPU time, right? Execution time. It's obviously right. So think about this. So we want to buy a fast computer, so which means that the execution time is to be small or low. Okay. So and then we learned about some how to calculate the CPU time. That means the execution time. So what is the equation? So I mentioned that this equation is so important, right? So you need to memorize actually. So in this course, we will use this equation. Okay. So what is the equation? T is the execution time. Instruction count multiplied by CPI multiplied by clock period is C. Okay, so that's what we learned in the previous class, right? So you need to memorize. You need to memorize this equation, right? So now, I will explain about the CPI part. So what is the CPI? So CPI, what is the definition of a CPI? It's a clock cycles per instruction, right? So actually we will learn about the instruction set architecture in chapter 2, right? But you need to know that, so actually a CPU executes a group of instructions, right? So when a high-level language code is compiled, compiled means that it's translated, then the compiler generates many instructions, and then the CPU execute these instructions one by one, right? So that's why the instruction count is uh, critical for the performance of a computer system. And then CPI. So this part, the CPI, uh, is also included in the performance equation. It means the CPU time equation, right? So also you need to memorize the definition. The definition of a CPI is the clock cycles per instruction, right? Then how can you measure? How can you measure the average CPI? So obviously, so we can count the clock cycles, right? And then we just divide the clock cycles with number of instructions, obviously, right? So it's a kind of the elementary level mathematics, right? So it's just definition, right? But also you need to understand that actually computer instruction, there are many kinds of instructions. So there are many different types of instructions. Actually, in the previous class, I mentioned the arithmetic instructions, right? The arithmetic means it's the add, the subtraction, addition, subtraction, multiplication, and division, something like that. And then the memory instructions like load and store, and then control instructions like jump and branch. Okay, so we will learn about these types of instructions in chapter 2. So anyway, so you need to understand that. So there are many types of instructions, right? And then these instructions exhibit different CPI, right? The average CPI can vary by instruction. Okay. So so there are many different kinds of instructions in an application. Then how can we calculate the average CPI? So for example, so arithmetic instruction, it occupies maybe the 50%. And then load store instructions occupy 30%, and then jump and branch instructions occupies 20% of 20% in an application. And then we can also provide some average CPI for a type of instruction. So for example, the arithmetic takes 2 cycles. So and then it's the maybe 5 cycles, and then so it's 3 cycles. Then how can we measure the average CPI? We can multiply the weight of this fraction, right, to the average CPI of a certain type of instruction. So this is also the simple mathematics, right? Right? So we can by multiplying the weight of instructions with the average CPI of a certain class or type of instruction, then we can calculate the average CPI, right? Then what does that mean? So it means actually the CPI can be different by different applications. Right. The application A may include the 50% of arithmetic, and then 30% of load store, and then 20% of jump. And the application B, the composition may be different. Application B may include the 40% of arithmetic, and then 50% of load store, and 10% of jump and branch instruction. Then and then average CPI, we can just measure the average CPI by the types of instruction. So in this case, because the composition of the instruction class is different, so average CPI can be different by applications, right? So also the CPI can be influenced by software, right? So we can calculate the CPI like this, just to memorize the definition of the CPI. Then I believe you can easily understand how to calculate the average CPI. Okay, so this is the example. So So this is instruction class. So that means the type of instruction, and then the CPI for the instruction type. So you CPI for instruction class. So it's a 1, 2, 3, right? And then this is the instruction count in sequence 1 and sequence 2. So you can just understand that sequence 1 is the application 1, so A1. Then this is the A2, application 2. So as I mentioned, different applications may have different fraction of instruction classes. So obviously, right? So because you can write the code, but this code is different, and different code will create different instructions, right? So this is the instruction count. Then how can we calculate the average CPI? By definition, right? By definition, CPI is the clock cycles divided by instruction count. So what is the total instruction count for sequence 1? It's 5, and this is 6. So instruction 2 has total 6 instructions. And then what is the number of cycles for sequence 1 and sequence 2? We can calculate, right? The instruction A, class A, the CPI for class A is 1. And then there are 2 instructions. The total cycles, 2, right? So 2, you know, 2. And then class B, CPI is 2. And then the instruction count is 1. So 1 multiplied by 2. And then 2 multiplied by 3 is a class C. Class C. Then total clock cycles, total number of clock cycle is 10, right? So, and then by definition, the average CPI is 10 divided by number of instructions, 5. Okay, so 2. And then for sequence 2, then with the same way, then we can calculate the average CPI, then it's 1.5. So this example shows the CPI. The CPI can be different by applications as software. So why did I explain this? So it's actually this is obvious, okay? Because as I mentioned, applications exhibit different fractions of instruction classes, okay? So that's why the CPI can be different by applications. So actually in the midterm exam, the midterm exam will include the similar questions, right? So then you can calculate the CPI like this way, right? So you can just understand the definition of CPI, the clock per instruction, okay? So this is the summary, the performance summary. And then as I mentioned, this equation is so critical, okay? The CPU time is instruction count. What is the instruction count? Number of instructions in a program, okay? So this is the definition of instruction count. And then multiplied by CPI, so that means the number of clock cycles per instruction, okay? So it's the average number of clock cycles per instruction, okay? It's a CPI. And then the second by clock cycle, this is the TC, clock period, okay? So using this equation, we can calculate the CPU time. So, and then why do we represent the this performance equation like this? Because using the terms of the equation, we can analyze the performance factors in a computer system. So for example, algorithm. So this is the software part. Software part influences instruction count, obviously, right? So if we write a different application, a different code, then these codes will have different number of instructions, right? It's obviously, right? So some code is so short, the length is short, then some code is long, the length is long, right? Instruction count is different. So it also depends on algorithm, okay, algorithm. And then, as I mentioned, so actually, so in this example, software can also influences CPI, okay? But possibly, okay? And then actually software primarily influences instruction count. So instruction count primarily depends on software part, application part. And then programming languages such as C or Java and some other languages, right? Programming languages also influence instruction count and CPI. Okay. Compiler also can change the number of instructions and CPI, right? So actually, so these are software part, okay? And then instruction set architecture. So we will learn about the instruction set architecture in chapter 2. So influences instruction count, CPI, and then the clock period. Also, as I mentioned, the clock period is mainly influenced by hardware, like some hardware design or semiconductor technology. So semiconductor, the process nodes. And then CPI is primarily influenced by architecture, the process architecture. So by analyzing the performance equation, that we can understand how each term influences the performance of a computer system. Okay. Okay, so and then we can use some different performance metric. So it's called the MIPS. So MIPS represent the millions of instructions per second. So what does that mean? So it's millions of instructions per second. So it is similar to the instruction count divided by time, right? So this represents the MIPS. So sometimes we can use MIPS for representing the performance of a computer system. Why? So intuitively, if the MIPS is high, what does it mean? Oh, this computer will execute more instructions in the same time, right? So intuitively, if the MIPS is high, then it represents, oh, this computer will execute more instructions in the same time. So what does it mean? So we can think that if the MIPS is high, then, oh, this computer is fast, which means the performance is higher intuitively, right? So is that true? So what is missing? So actually, so think about the algorithm. The algorithm affects instruction count. So which means, oh, this is the same application, right? Well, maybe it can be different. So, okay, so just ignore this. So just ignore algorithm. So for example, programming language also influences instruction count. So what does that mean? Oh, this is the same application, and then, oh, I compiled the same application with the C compiler. And then I compiled the same application with Java and C. Then the instruction count can be different. Okay, so what does that mean? Even though the application is the same, the instruction count can be different. Also, the compiler also influences the number, the different instruction count and CPI. Okay, so for example, the problem is that so I will explain why using MIPS we cannot directly measure the performance of a computer system. So for example, so this is the same application A, right? And then we can apply the different compiler optimization level. So if you are familiar with GCC, it's a GNU C compiler, then GCC actually has many different compilation options, right? So like we can apply the different optimization levels. Okay, so we can just compile this same application using -O0 option. So there's no optimization. Then this compiler will generate some compiled code. But this compiled code can include many instructions. No, many instructions. And then the same application A can be compiled with the optimization. So the high optimization levels like -O3. Then this compiler will generate the smaller instruction count. Okay. So because the instruction count is different, the execution time can be also different, right? So let us assume that this when the application A is compiled with the no optimization option, then it generates the 100 instruction, right? And then so when the A is compiled with the highly optimization level, then it generates the 20 instructions. And then so this binary this is just the assumption. So let us assume that this binary takes 5 seconds. How about this? This is the maybe 4 seconds. Okay. So we know, this option is better, right? Which means that the execution time is low. But we can compare the MIPS, the number of instructions per second. What is the, not MIPS, so the number of instructions per second. What is the number of instructions per second? So this case, it's 20. This case, it's 5. Do you understand? So if we just compare number of instructions per second, right? You can find that, this number is larger, it's higher, right? But which is better? So which means, that means which performance is higher? Which performance is higher? This one, right? Why? Because by definition, it takes only 4 seconds compared to 5 seconds. But MIPS is low. So when I explain about the MIPS, so I mentioned that we can intuitively think that if the MIPS is high, then performance is also high intuitively. but it's not always true. So this is the example, right? So in order to use the MIPS for performance metric, then we need to assume that we need to use the same ISA, the instruction set architecture. Also, we need to use the same compiler options, and then also the same compiler. Okay, because the MIPS only just consider the number of instructions, but when we compare the performance, so we need to actually consider the execution time. So do you understand? Okay, so this is important. So just to understand the definition. So definition, the performance is the inverse of execution time. So this is the definition, right? And then in order to use the MIPS, we need to consider the same ISA and then same compiler options, right? Because actually the execution time is calculated by instruction count multiplied by CPI and multiplied by TC, okay? Actually, many factors, like the CPI or instruction count and TC, these factors influence the performance of a computer system. Okay. Okay. So if the ISA is the same and then compiler option, well, also the compiler is the same, we can use MIPS as the performance metric. Okay. Otherwise, we cannot use. Okay. 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 So we learned about the performance metric of a computer system. So now I will explain about the power. So until this point, I explained about the performance of a computer system. So now, what is the power? It's the cost. Cost of a computer system. Why? If a computer system consumes the more power, then so we need to pay more, right? So it's just the electric power, right? And then if actually the computer system is an electric device, right? So if the electric power is consumed, so we need to pay. It's just money. It's a cost. So power is related to the cost of a computer system, right? Then why? And then, as I mentioned in the previous class, we need to increase the performance of a computer system because everyone wants to use faster and better computer system, and we need to reduce the cost of a system. And then power is the cost of a computer system. So this is very important factor also. 여기 자리 있어요. 자리 여기 앞에 있어요. Okay, so which means we need to reduce the power consumption of a computer system. So let's see the power trend of the CPU. So the very old, so you know this x-axis is the time, the years, and then y-axis is the clock rate, and then also you can find that this is the log scale, and then another y. So this y-axis is the represent the power, and then this is the linear, right? So actually, where is this number? This number represent the clock rate, and then this black line represent the power consumption of a CPU. So different CPU. So very old CPU. So 8286. So old CPU. So you can find the year here. So what is the power? What is the power consumption of this CPU? It's just 3.3 watt. So this number, 3.3 watt, is lower than our smartphone CPU, right? So usually the actually it depends on the some operation mode, but usually the maximum power consumption of our mobile CPU is around the 5 watts, and then recently it's higher, right? But you can find oh, this is so the power consumption was so low. Also, the clock frequency is also so low. So what does that mean? The performance is extremely low. So you can find that the power consumption is slightly increased, but also the clock frequency is also slightly increased. But at this point, the power consumption had increased dramatically. Okay, so like the Pentium Pro and Pentium, and then Pentium Pro, and then you can find that the power consumption of a CPU increases dramatically. But also we can observe that. So during this period, we can find that clock frequencies was the 200 megahertz. And then at this point, it's the 2 gigahertz, right? So fast. So what does that mean? If we just compare the Pentium Pro and then Pentium 4, the performance is dramatically increased. You know, the clock frequency becomes 10 times of Pentium Pro. So, right? But also you can observe that power consumption is also increased, right? So what does that mean? So actually the power consumption is also influenced by many factors, but primarily the power consumption is influenced by hardware part, right? Hardware design, and so semiconductor technology, and right, something like that. So, but intuitively, so we can think that, oh, in order to increase the performance, of a CPU, then the power consumption is also increased, right? So there's no ideal thing in the real world, right? There's no uh, free riding or some free stuff in the real world, right? So in order to increase the performance, which means so the cost is also increased. So at this point, the clock frequency reaches the 3.6 gigahertz. Then you can also observe that the clock frequency is saturated, right? So it can be increased, but what is the problem? What's the problem? If we want to increase the clock frequency more, then power consumption will be also increased. So that's why we cannot use higher clock frequency in a CPU design, right? So actually, uh, maybe until the 1 or 2 years ago, the clock frequency of Intel CPU was around the 3 or 4 gigahertz. So very similar to this level, right? And then it is because Intel did not want increase the power consumption of their CPUs, right? That's why Intel just used the similar clock frequencies. But recently, the Intel also increased the clock frequency, right? Because so they want also develop they also want uh, develop the high performance CPU, like and then the recent CPU can work with the 5 gigahertz, around the 5 gigahertz. But what's the problem? Power consumption. Power consumption is also increased. So if you are interested in the hardware, then you maybe heard about the TDP, not TDW, TDP. What does it mean? TDP means thermal designed power. Okay. So actually, the Intel maintains the TDP level as the less than 100 watt. Okay. So which means that in the typical case, the Intel CPU consume 100 watt of power. But recently, actually, the TDP of Intel CPU is also high because Intel increases the clock frequencies of their CPU, right? So what can you observe? Power. Power is a very critical part for CPU design. Also, the performance is also influenced by power, okay? And then power is very critical design constraint, okay? Okay, power is very critical actually, okay? So let's see the power equation. So CMOS technology, so it means the semiconductor technology, and then it is known that the power is actually proportional. So it's not an exact equation. The power is proportional to the capacitive load and then the square of supply voltage and frequency. So what does it mean? Capacitive load, the supply voltage, and then frequency. So it is, as I mentioned, so it is related to the hardware design, right? So actually the hardware consumes the electric power, right? So the power is proportional to the capacitive load and the supply voltage and the frequency. So what is capacitive load? It's total capacitance of CPU. What is total capacitance? So uh, when you learned about the physics, electric physics in high school, right? Then maybe the education was changed. But I believe, so if you learned the electric physics in high school, then actually the circuit has the three components like R, resistance and capacitance and inductance, right? Actually, inductance is represented using L, okay? So, and then the capacitance of a circuit is proportional to the size, the size of semiconductor devices. Okay, so if you see the chip photo, actually it's called the die photo. Okay, because chip is called the semiconductor die. Right, where is the die? So this is a die photo, right? Okay, so this is the semiconductor CPU, right? And then actually we can measure the size of this die, right? So like it's a height multiplied by width, right? So this is the size of the semiconductor devices. What size of die or die, DIE, okay, it's called the die. And also it's a size of a chip, okay? The capacitance is proportional to the size of die. Okay, so which means if a chip is large, then capacitance is also increased. So for example, if we use the large GPU chip, the GPU chip includes many transistors. So which means also GPU actually with the very high capacitance. Okay. The power is, which means the power is proportional to the size of a die or size of a chip. And then supply voltage. So in order to run the electric circuit, so we need to provide the supply voltage. It's called the VDD. Okay. So actually, the electric devices works using the difference in voltage, right? So we learned in the electric physics. Okay. So the power is proportional to the square of supply voltage. Okay. And then clock frequency. So because the clock signal changes from 0 to 1 or 1 to 0 periodically, so which means that the voltage level changes periodically. So when the voltage level is changed, then power is consumed. So what does frequency mean? Frequency represent, clock signal is changed many times in a unit time, right? How many times? So many times in a unit time. So if the frequency is high, then a circuit will consume more power. So this is the power consumption equation. Okay. So, and then when the CPU is advanced, so you know the actually the power is also increased. So which means, but we can observe that so from 200 to 2000, the frequency is actually from this point, the frequency is increased around 1,000 times, but the power is just increased 30 times. So it is because the voltage level, we can reduce the voltage level when we use the smaller transistor. So you may be this is a little bit tricky, but because this information is related to hardware, so not software. So real hardware devices, okay. But it's just the common sense, right? Right. So it means so everyone says that the semiconductor technology is so critical, right? So, the the USA, the United States, so actually, so need to, they want to uh, develop their semiconductor technology industry like Intel, right? Also, the South Korea is the same. The South Korea, actually, so there is a very big semiconductor company like Samsung, right? Samsung. So they also, uh, Samsung makes also a chip. Okay. So also the Taiwan has TSMC, right? So everyone says semiconductor technology is critical. It's so important. But why? Why? Because power. So, and then if we use a smaller transistor, a smaller CMOS transistor, which means that we can, so this, you can find some numbers like 3 nanometer technology, 5 nanometer technology, or 2 nanometer technology. And then this number represents the size of a transistor, right? And then actually these companies such as Intel, TSMC, or Samsung try to develop the advanced semiconductor technology, which means that they try to reduce these numbers. Okay, so they try to develop the smaller transistors. And why? So if we use a smaller transistor, then firstly, we can reduce the voltage, the supply voltage. And then we can increase the clock frequency. So it's good, right? We can if we just reduce the supply voltage, then power is also reduced. So power can be reduced. Or the cost can be reduced. And then if we increase the frequency, then we can increase the performance. So which means if we use a smaller transistor, then we can increase the performance, right? It's a very good thing. So that's why semiconductor technology is so critical. Okay, it's very critical actually. So using this equation, we can just compare the power consumption of two different systems. Okay, and then as I mentioned, the CPU design can be constrained by this power. Okay, so we actually this is a very critical part. So this is called the power wall. Okay, and then okay, so I will show this one. Actually, but this is the more detailed, the more exact the dynamic power equation. So I mentioned this is the dynamic power. Actually, in a CPU, there are two kinds of the power consumption. The first one is dynamic power, and then second one, what is the opposite word of dynamic? Static, right? So we can observe static power. Dynamic power represent when the voltage level is changed. Okay, so if you took the digital logic design course, so in order to make some result, then we can just change the voltage level, like the 1 to 0 or 0 to 1, high to low or low to high. So the voltage level can be changed. Okay, then we can just process the digital data. Okay, so dynamic power means the power consumption, power consumed by dynamic operation. So which means that the signal level, the digital signal level is changed. When the digital level is changed, then dynamic power is consumed. Okay. Static power. Then this is the opposite meaning. Static power means even though the voltage level is not changed, power is consumed. Right? It's called the static power. But actually in the old generation of CPU, then we just consider the dynamic power. So it is because actually when we design a circuit, the CMOS circuit is composed of PMOS transistor and NMOS transistor, right? And then actually the one of transistor is off. Off means that it's disconnected. If the circuit is disconnected, then the power is not consumed, right? Because the power is the current multiplied by voltage, and then if the circuit is disconnected, there's no current, so power is 0. So actually in a CMOS circuit, the CMOS circuit is composed of the PMOS and then NMOS transistors. Actually, in this design, one of transistor is off. So actually, in a steady state, current does not flow. So because I is 0, then P is also 0. So actually in the old generation, we did not consider about the static power. But now we needed to consider static power also. So what does that mean? Actually, even though the transistor does not work, so which means that the voltage level is not changed, power is consumed, which means the current flow from NMOS to NMOS transistor to PMOS transistor to NMOS transistor. Okay, it's called the static power. So static power means that we do nothing with the CPU, but power is consumed. Okay, so why? Because as the transistor size is reduced, then transistor cannot work as the perfect switch. So even though the transistor is off, the current flows. Okay. So, and then because of this, the actually, even though we use the transistor, semiconductor technology, then we cannot benefit from the power consumption. We cannot. So actually, in the old generation, so this is the red line represent the technology node. So you can find that. So this is the nanometer. So it's a technology node. And then I mentioned that if this number is reduced, so which means that the size of transistor is also reduced. And then this blue line, the blue line represents the power consumption divided by square nanometer. So it means the power consumption in the same area, same chip area. So you can observe that when the technology node is advanced, so which means that the transistor size is reduced, but the power, this is called the power density. Power density is nearly the same. Why? Because think about this equation, but if we use the smaller transistor, then we can reduce the voltage. But we can increase the frequency. But anyway, the benefit is that in the same area, the power density is the same. So this is, and also if the transistor size is reduced, we can include more transistors in the same area, obviously, right? So device becomes smaller, then which means we can put more devices in the same area, right? So this is a good thing. So we can include more devices. Also, the frequency can be increased, but power is the same. But it's increased. So actually, at this point, so this is called the Dennard scaling. So Dennard is the name of a person. It's a semiconductor and maybe it's a scientist. Okay, scientist. Okay, so actually this is called the Dennard scaling. The Dennard scaling means that even though we reduce the size of a transistor, but the power density is the same. So it means we can use better CPU even though the power is the same. It's very good news. It was a very good news, but Dennard scaling ended, right? So at this point, you can find that the power density is increased, has increased. Okay, so which means so we can develop better CPU using advanced semiconductor technology, but the power is also consumed more. Until this point, we can develop better CPU using advanced semiconductor technology, and then power consumption was the same. It was free, but now it's not free. Okay, so this is the actually very critical problem. Okay, so cool. You know, so you may think that, oh, why? So it's just the power. So, but the cost is very critical because think about the companies. So like Google, uh, uh, Google has very big data centers, and then a data center size is very large, which means this data center includes many computers. These many computers consume much power. Like the actually a data center consumed like uh the 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 electric power similar to the nuclear plant, right? So data center consume much power. But if this power is increased, then Google needs to pay more money. They need to avoid this. So that's why power is so critical. It's money. Okay. So this is the problem. So the processor architecture has been changed. So, so this graph shows the performance of uniprocessor. So what is uni? So which means the single. So in this graph, so you can find that the y-axis is also the log scale, the x-axis is the year, so which means that, and then, the performance is increased linearly, so, and then it's a log scale, so which means exponentially. The performance is increased exponentially. So it's about the 20% per year, it's about the 50% per year, 23, 12, 3.5. So what can you observe? So dramatically increased at this period, but it's slow down, nearly saturate. So which means the performance, the performance of the single core is nearly the same. It is because this graph, the frequency is nearly the same, right? Actually, from in Pentium 4, so it's 2004, right? So you may think that, at least to 2004, even though from the 2004, so it's increased, but this increase is caused by architecture, the CPU architecture. Okay, at this point, it's saturated. So why? It's because of power. Using the smaller transistor, we can increase the frequency. But problem is that if we increase the frequency, the CPU will consume much power. So which means we need, so think about this. So you have a desktop computer, and the desktop computer consume the power similar to the air conditioner. So then you cannot use this desktop computer, even though this computer is so fast, right? So because of power, we cannot, it we can increase, but if we increase the performance of a single processor, then this single processor will consume much power. This is the problem. Then how? What did we do? What should we do? We can. It's difficult. It's difficult to increase the ability of a single core. So which means the performance of a single core. So in the real world, it's not easy to increase the ability of a single person. Then what should we do? Right. So we need to increase the number of employers, right? Uh, no, number of employees, right? Number of employees, which means CPU, then to increase the performance, we can increase the number of cores, right? So it changes to the multi-processors, multi-core processors. So multi-core microprocessor, it means there are multiple cores in a chip, okay? So, and then actually you can think that, oh, my CPU is a multi-core CPU, and then actually every CPU is a multi-core CPU, right? Even my smartphone CPU has many cores, the multiple cores, but it is because of power consumption. So at this point, the frequency is saturated, and then the CPU vendors include multiple cores in a chip. Then by doing this, they try to increase the performance of a CPU. But you may think that, oh, really? Why? We learned about the CPU time, right? So CPU time is the instruction count, CPI, and then TC, right? Instruction is it's determined by software. CPI, it's the same, nearly saturate. TC, it's a nearly same. CPU time is the same. How? How can we increase the performance? So, this graph shows the performance of uniprocessor. Then if we just mention the performance of uniprocessor, then it represents the CPU latency. So CPU time. So actually the inverse of CPU time, right? But when we mention the performance of multi-core CPU, then this performance represents the throughput. So what is throughput? What is the definition of throughput? It's amount of work done in a unit time, right? Actually, using the unicore, so single core processors, it cannot reduce the CPU time of a single thread, single application. Was actually more exactly single threaded application. Okay, because same. it cannot reduce, right? But using the multi-core architecture, there are multiple cores, then we can increase the throughput, the amount of work in a unit time. Obviously, right? Then what is required? I mentioned the single-threaded application. So in order to increase the performance of application, then application needs to support parallel executions or parallel processing. Okay, so which means a single application needs to create multiple threads, okay, in a CPU. So what is required? We require parallel programming. So Actually, using the multi-core architecture, we cannot increase the single core, the performance of a single core, or the performance of a single-threaded application. But in order to increase the performance, we need to develop the parallel applications, right? But it's not also easy. So parallel programming is not easy compared to the single-threaded single thread programming. The parallel programming is not easy. So there is some overhead. But think like actually it's a similar to the real world. So the team A has the 2%, and then team B has the 4%. Then performance is two times in the real world. No, absolutely no. Why? Even though team B has four members, but the performance is actually lower than the double. Why? There are many issues, such as the communication issues. It's the same to the computer system. So there are many cores. So in order to complete the task of a single application, then these cores need to communicate. So which means that the data needs to be exchanged. But this communication overhead can be high. And because of this communication overhead, the performance can be degraded. Also, another reason is that a certain task cannot be parallelized. Also, if we uh, uh, our work can be composed of many tasks, and then these tasks can have the dependencies, right? Then we cannot parallelize a certain task. So in this case, we cannot increase the performance. Okay. So also it's the same issues in the multi-core architecture. If the application or task cannot be parallelized, then we cannot increase the performance. Okay. 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 So now, nearly 5 minutes. So I will explain about the benchmark. So until now, so we learned about the performance. Also, we learned about the power, the cost factor in a computer system. Then how can you measure actually? How can you compare? So we learned about the T equal instruction count, CPI, and then TC. But this part, instruction count is influenced by software. So which means if we use different software, then this number is changed. So what is required? We require the same application, the standardized application. So using the same application, we need to compare the performance of different systems. Why? Because we need to make this part the same for the different machines, right? Do you understand? So these applications, so we use the standardized applications for measuring the performance of computer systems. And then these applications are called benchmarks. Okay. So if you are interested in hardware, then you can frequently heard about you can hear about some benchmarks, right? So using the benchmarks, we can measure the performance. So it's the same to the CPU. The CPU has the benchmark for measuring the performance. And then it's actually the most popular CPU benchmark application is the spec benchmark. Okay. It's just a bundle of applications. And then using the same bundle of applications, we can measure, we can compare the performance of different computer systems. So this is the example. So this is the application name. And it's an application name. You can find the multiple applications. So as I mentioned, this is a bundle, the bundle of applications. And then Now you can find the instruction count and then CPI and then clock period like this. Also by using these numbers, we can calculate the execution time. Okay. Then how can we measure the performance? So what is required? Other system, like reference system, right? As I mentioned, we can just, in order to measure the performance of a computer system, we need to compare, right? It's the same. The spec benchmark provides the execution time of a reference system, okay? And then we can measure the execution time using these applications, right? Then we can calculate the spec ratio or spec score. So, for example, for the per bench, this is the execution time of my machine. This is the execution time of reference machine. Then what is the performance of my machine compared to the reference machine? It's 1774 divided by 627. Then this number, we can get this number, 2.53. So what does that mean? Compared to reference machine, my machine is faster 2.83 times for per bench, right? So we can calculate this number for different applications, right? Then by performing geometric mean, we can calculate the spec score. So this score represents the performance of my machine. So if this score is higher, so which means the performance is higher, right? So we can compare. We can compare the performance like we can measure the performance like this. Okay, so we can use the spec benchmark for measuring the performance. Okay, so these are benchmark. Okay, so I will stop here. Any questions? Okay, thank you for your attention. See you in the next class. 감사합니다.